Potato is here to represent our atom. In the Bohr model, electrons can release energy as a photon, allowing the electron to move down to a lower energy ring. The energy of the photon is equal to the initial energy of the electron minus the final energy of the electron. In the photoelectric effect, the electrons absorb the incoming photon as it hits the material. If the amount of energy absorbed by the electron passes the work function, it gets knocked out of the material. Looking at the equation, the maximum kinetic energy of the emitted electron is equal to Planck's constant times the frequency of light minus the work function. Another relevant equation is E equals hf because it represents how energy is quantized, with each photon acting like a pack of energy.
When the firework explodes, it provides a big amount of thermal energy. The energy is absorbed by the electrons. When the firework is lit, the electrons go into an unstable excited state. They want to return to their lowest energy level, and to do that, they have to get rid of all the extra energy by spitting out a photon. The colors change depending on the amount of energy they have to release / get rid of. For example, higher energy equals short wavelength, which is blue / violet, and a lower energy is equal to a longer wavelength, which is equal to a red or orange color.
Another common application of the photoelectric effect is in a digital camera, specifically in its lens, and the image sensor within it. The image sensor within a lens is made of a semiconductive material like silicone. It is there to represent the pixels of the images that you see after you take the photo. And click, you've taken the photo. What happens next? Photons from the area around you go through the lens and hit the sensor in very specific points along the grid, creating pixels. You may see here, some pixels get hit with more photons than others. As you can see here, pixel A was hit by 2 photons, while pixel B was hit by only 1. Because of that, pixel A will have a higher amount of energy, and a higher amount of energy means a brighter spot. So that pixel will be brighter in the image, and so on and so forth. But let's get closer. Let's look at this at an atomic level. Here we have an atom with several electrons orbiting it. When the atom is hit by the photon, it absorbs the energy within it. The energy, of course, must be emitted afterward, and the electron then goes through the semiconductive material to the electric sensor beneath the image sensor. This is what ultimately creates the pixel. Stay tuned for our behind the scenes and outtakes.
E is the photon's energy. H is Planck's constant. And F is the frequency. E is directly proportional to its frequency, and then H is a constant.
So, how much energy will this electron gain when the photon is absorbed? Let's find out. Let's do a sample calculation. Let's say the photon's frequency is a good 6.0 times 10 to the 14th power hertz. Yeah. With that, we can just use Planck's constant and multiply by that. So that's going to be 6.0 times 10 to the 14th hertz times 6.63 times 10 to the negative 34th power. And those are joule seconds. What does that equal? That is going to equal 3.98 times 10 to the negative 19 joules. The seconds cancel out for the hertz. And because it's joules over seconds, cancel. That's how we got joules. And this is how we got energy. So this electron is going to be getting a very tiny amount of energy, but a lot for this little guy. And that will make him get excited, and he'll go up here, become this little electron basically, and then a photon will fly out of a different frequency. Yay! So, what is the color of the firework gonna be? Well, we need to find out the wavelength if we want to know the color. So let's say the frequency is 6.0 times 10 to the 14th. Giant. That is a large amount. That is above tera. And so we just plug it into the equation. So speed of light is 3 times 10 to the 8 meters per second. Then we're going to have 6.0 times 10 to the 14 hertz. Let's do the math. Okay, it's just going to be 1/2 times 10 to the -6, not 7 meters. Let's make this better for us. Okay, let's say this is 500. Let's convert this to nanometers. Okay, ignore that 0 point. Yeah, so this is to convert to nanometers, we're gonna go from 0.5 times 10 to the -6. It's actually 7. It's not 7. And then just go, yeah, 10 times to the -9 meters, or just 500 nanometers, which I know because I was staring at so many laser beams that this is green. Hard at work or hardly working? Scribble. And here we have the genius work of engineering brought to you by me. Scribble, scribble, scribble. Drawing. Wow, pictures. Thanks for watching.